So last thing we had talked about first semester was polynomials, right? That was the last topic we had talked about. So the last thing we talked about in semester one, we talked about the topic of polynomials. We talked about adding, subtracting, multiplying, dividing, factoring, and solving polynomials primarily. The place where we're going to pick up in semester two is we're going to spend some more time talking about factoring and solving polynomials, because there's still a lot of polynomials that we didn't come up with a decent factoring method for, and as a result don't have any good solving methods for. So that's an important piece. And really the goal for this first chapter in semester two is to develop some methods for factoring and solving polynomials. So separate from those methods from first semester. Oops. From, not form. Okay, so that's really what we're going to be doing for at least this first week, is kind of working towards this idea. Okay, so just to kind of give us an idea of where we're headed and where we're kind of building from. Now, some of our methods for factoring and solving of polynomials that we developed in first semester are still going to be helpful at places in second semester. So I want to take a quick pass by and talk about those factoring methods, because once we've got our polynomial factored, the solving isn't difficult, right? We just set each of the factors equal to 0 and go from there. So in semester one, when we talked about factoring polynomials, what I did is I drew out that big factoring tree for you guys, right? I'm going to draw that again just to kind of show you where in this factoring tree we're going to be adding on to. Now, if you have this already in your notes from first semester, that's fine. If you want to rewrite it again because you're like, yo, my first semester notes are long gone, totally on you, okay? So worth remembering that when we drew this, I encouraged you guys to turn your paper landscape style, because this factoring tree gets wide, but it doesn't get too terribly deep. So the first thing that we do is we look at the number of terms that our polynomial has. And there were three possibilities. We dealt with situations where we had 2 terms, where we had 3 terms, and where we had 4 terms. in the two-term situation, the first thing we check to see is if our polynomial was a difference of two squares. If the answer was yes, we factored it using that, and then we went back through the two-term branch to see if there was any more factoring. If it wasn't a difference of two squares, then we check to see if it's a sum of two cubes or difference of two cubes. If the answer was yes, we had to go back through that two-term branch again to see if there was more factoring. If the answer was no, we finished. That completes the two-term branch. So for three terms, the first thing we did was check to see if it's in the quadratic form. If it wasn't, there was nothing more we could do. If it was, then we're going to factor this thing like a quadratic. So there's two situations that we could deal with if it was quadratic. That's where the leading coefficient is 1, and where the leading coefficient wasn't 1. So if the leading coefficient is 1, we can do that short factoring technique where we need to find the two things that multiply to give us the constant term and add to give us the middle term. And if the leading coefficient wasn't 1, then we had to do that long factoring where we had to find the two numbers that multiplied to give us the leading coefficient times the constant term and added to give us the middle term. And then we broke the middle term up using those two numbers and then did factoring by grouping. So if we can do the short factoring, then we have to go check the two terms. And if we can do the long factoring, again, we have to go check the two terms. If we can't do the short factoring or long factoring, then we're just done. And then the last branch that we had to deal with was the four-term branch. So the only option we have with the four-term ones is, can we do a factor by grouping here? If we can't, there is nothing more for us to do. if we could, then we had to go and check the two-term parts to see if there was any more factoring that we could do. So that was the factoring tree that we built for first semester. Right? You guys kind of remember doing this or using this, hopefully. Now, there are some places that we couldn't do anything, right? For example, if I wasn't in the quadratic form, there's nothing for us to do. Or if I couldn't factor by grouping, there wasn't anything to do. Or if we had 5 or more terms, oops-a-daisy. There wasn't anything more to do. What we're going to do over the course of this next week or so is fill in these kind of parts of our factoring tree. So if I have a 3-term polynomial that's not in the quadratic form, it might still be factorable. We're going to develop some methods to handle that. Or if I have a 4-term polynomial that can't be factored by grouping, it might still be factorable. We'll develop some methods to handle that. If I have a polynomial with 5 or more terms, could still be factorable, we're going to develop some methods to handle that situation. So that's what we're going to be working on over the next week or so, is figuring out some methods to kind of extend this factoring tree and be able to factor more polynomials than we could using just these techniques. Now, in the course of factoring some of these other polynomials, might I use some of these techniques along the way? Sure. Would I necessarily have to? Maybe not. But I may still end up using some of these factoring techniques as a subpart, as part of a larger factoring problem. We'll deal with that when we get there. Okay? But that's the idea. That's kind of where we're picking up from, what our goal is for this chapter, at least the first and the majority of this chapter. There'll be a little bit more at the end. But this is a pretty long chapter. Some of these techniques are not easy. Well, I shouldn't say that. They're relatively easy. They're just not fast. Potentially could take some time. Okay? So what I want to do next is just a little bit of vocab. And then we'll start connecting what we've been doing to what we're trying to do with some examples. All right. So let's say we have x squared plus 7x plus 12. That's an example of a polynomial, right? Can we factor this polynomial? Should be something that's easy for you to do. What does this factor to? The two numbers that multiply to give us 12 and add to give us 7 are 3 and 4. So my factored form is x plus 3 and x plus 4. So this polynomial generates these two factors, right? Everybody okay there? What if I have x squared plus 7x plus 12 equals 0? This would then be a polynomial equation, right? What are the solutions to this polynomial equation? -3 and -4. How did you find those so quickly? Great. So we use the factors that we established in the previous step, set them equal to 0, and solved, right? So if I have something like y equals 7x plus 12, I could graph that, right? What are these 2 points called right here that I've drawn? Those have a name, right? What's special about those 2 points? They're crossing the x-axis, so we call them x-intercepts. Guess what these 2 x-intercepts are going to be? It's -4, 0 and -3, 0. So let's say we have the polynomial function f of x is equal to x squared plus 7x plus 12. What do I get if I do f of -3? What do I get there? What does f of -3 tell me to do? Good. Substitute -3 in for x's. Exactly right. What value am I going to get when I do that? It's going to give me 0, right? Because I know the solution to the equation x squared plus 7x plus 12 equals 0 is -3. So if I plug -3 back in, I should get 0, right? Similarly with f of -4. So we call those zeros for the polynomials. So notice that the factors, the solutions, the x-intercepts, and the zeros, these are all related to one another, right? If I know one of them, I can find the other ones. Everybody agree with that? Which one of these would be the most maybe the most valuable ones to know? Which ones are going to be the most inclusive? The solutions are going to be the most inclusive ones. Why would the solutions potentially contain things that the other ones do not? Because a solution you can get an imaginary result for, right? When we factored things, did we ever have i's in our factors? No, right? We're not going to be able to find those using the factoring techniques we have. if you graph something, are there going to be points with i's in them? Definitely not, right? If you plugged an I into the function, well, I guess you would get zeros there, but it's really not obvious what to do with that. But that's the takeaway here, is the imaginary things are hard to find, right? You really need to be able to solve to find the imaginary things. It's tough to find those from factoring. In fact, it's impossible to find them using the graph. Well, maybe I should say not practical for us to find them using the graph. And really, there's not a good method for finding them using the function. Solving is going to be the key for us to find those imaginary pieces. But I can find the non-imaginary pieces using the other forms, right? I could use the x-intercepts and have a good idea of the real solutions. And if I know the real solutions, I have a good idea of what the factors would look like, right? Does that feel okay here? A lot of what we're going to be doing in this chapter is trying to use a workaround by looking at, instead of factoring a problem, maybe I'll think about this as a graphing problem and look at where the x-intercepts are. And maybe the x-intercepts will give me some information about what those factors might be or what those factors might look like. So we're going to take advantage of the relationship between factors, solutions, x-intercepts, and zeros to really kind of take full effect and really try to be able to factor as many things as we can. All right. So let's look at an example here. Let's say we have the polynomial x plus 1 times x plus 2 times x plus 3. This looks like a multiplication problem that we did last semester, right? So to multiply something like this out, I can just use the associative property and pick two of these factors to multiply together. So maybe let's just pick the first two factors to multiply together first. How do I multiply two things together like this, x plus 1 times x plus 2? What's the name of the method that I use to do that? FOIL, right? So I get x squared plus 2x plus 1x plus 2 times x plus 3. And I notice that I can combine some like terms there. And just write x squared plus 3x plus 2 times x plus 3. Everybody is okay with that? So far, so good? Now I could multiply these two things together. Last semester, what did I recommend using to multiply two things like this together? I made that grid, right? Do you guys remember making the grid? Everybody kind of remember doing that? So what I can say in conclusion then is that this gives me the polynomial x cubed plus 6x squared plus 11x plus 6. Everybody agree with that? Harley. Of course. Now suppose I ask you to factor this polynomial. Well, I guess it has 4 terms. So the obvious thing would be to try to group it. Everybody agree with that? So from the first group, I can take out an x squared. In the second group, though, the only greatest common factor is 1. There's nothing in common between 11x and 6 other than 1. Can I continue factoring this, though? Why not? Those two are not the same thing, right? One is x plus 6, the other is 11x plus 6. Because those two parts aren't the same, there's no more, I can't finish factoring this by grouping. According to my factoring tree, I would say that this is not factorable, right? I'd be done. There's nothing I can do. Everybody agree with that? Let's write that. But would I really, is this thing really not factorable? How did I get that polynomial again? I multiplied x plus 1 times x plus 2 times x plus 3, right? Sure looks like it's got to be factorable. X plus 1 times x plus 2 times x plus 3 is equal to that. Look, it's factored. But how would I do that? I can't use grouping. We just tried to factor by grouping, and it does not work. There has to be some other way to do this. This is an example of the kind of thing that we're going to be filling in the blanks for this week. Okay? So there's got to be some other way to do this, right? Clearly it factors because, well, we multiplied 3 things together to get it, so there's got to be some way to take it apart to get those 3 things back. Everybody agree with that? So we're going to need some new tools to do this. The first tool is called the factor remainder theorem. This says that if I have a function p of x divided by some other function q of x, let's say as remainder 0, then q of x is a factor of p of x. Everybody okay with this, what this is saying? If I have 2 polynomials, and I divide them, if I get a remainder 0, that tells me that the dividend is factorable into something times the divisor. So let's just do this intuitively with some numbers because it makes a ton of sense if we think about this numerically. Let's say 18 divided by 3. Well, if I do this like long division style, I would get something like this, right? Everybody agree? So I know that 18 divided by 3 is equal to 6 with a remainder of 0. So can I turn this into a multiplication problem? Sure I can. 18 is going to equal that divisor times the quotient, right? This looks like a factored form for the number 18, doesn't it? That's precisely what the factor remainder theorem is saying. Except instead of doing this for numbers, we're going to do this for polynomials. So let's say we ask, is x plus 4 a factor of x cubed plus 6x squared plus 11x plus 6? So how can I check this? Is I just need to check to see if this has remainder 0. If this division problem has a remainder of 0. If it does, then yes, that thing's a factor. If it doesn't, then no, it's not a factor. So what's going to be the easiest way to divide these two polynomials? We talked about this last semester, right? So you can use long division, but if I look at the divisor, it's a degree 1 with leading coefficient 1, so I can do the synthetic division shortcut on this. This is why I really emphasize the synthetic division, because we're going to use it a lot in this chapter, as it speeds things up considerably. So the synthetic division setup, I draw my bar that looks like this. What number goes on the outside of this division bar? Not 1, not 4, negative 4. How do I get that number that goes out there? I set the divisor equal to 0 and solve. So x plus 4 equal to 0 has a solution of negative 4. Everybody's okay with that? What numbers do I write on the inside? 1, 6, 11, and then 6. Where am I getting those 4 numbers from? They're the coefficients of the dividend, right? Everybody's okay with that? Notice I didn't have to include any zeros there because I don't skip any terms in my dividend, right? I go from degree 3 to degree 2 to degree 1 to constant term or degree 0. Right? So there's no need to include any extra zeros there. So I start my synthetic division by just bringing the first number down, and then I multiply the negative 4 by that number and write it in the next spot, and I add down. And then I just continue that process until I filled in all the blanks. So 2 times negative 4 is negative 8. I add down, I get 3. Negative 4 times 3 is negative 12. I add down and get negative 6. My remainder is not 0. What does that tell me? It tells me x plus 4 is not a factor of x cubed plus 6x squared plus 11x plus 6. But we knew that already, right? That polynomial factor to x plus 1 times x plus 2 times x plus 3. We knew x plus 4 wasn't a factor, but this confirms it, right? What if we ask, is x plus 3 a factor of x cubed plus 6x squared plus 11x plus 6? Well, we'll do the same thing. We'll test this by using division. What number is going to go outside of our synthetic division bar? Not -6. I use this one, -3. Okay? And what numbers are going to go on the inside? One, 6, 11, 6, just like before. Sierra, question? Okay. And then we'll just start by bringing that first number down. And -3 times 1 is -3. I add down, giving me +3. -3 times +3 is -9. I add down, giving me +2. And -3 times +2 is -6. I add down and I get 0. So that tells me that x plus 3 is a factor. And in fact, it tells me a little bit even more than that. So if x plus 3 is a factor, I know that x cubed plus 6x squared plus 11x plus 6 is equal to x plus 3 times something. Right? Some other polynomial. Everybody agree with that? What is that polynomial going to be? I have it right there. So remember that this is the constant term, the x coefficient, and the x squared coefficient. Now, if I look at x squared plus 3x plus 2, can we factor that? Yes. Right? That's in the quadratic form, right? Its leading coefficient is 1, so I just need to find two numbers that multiply to give me 2 and add to give me 3. Those two numbers are 1 and 2, right? 1 times 2 is 2. 1 plus 2 is 3. And look, it's factored. So, kind of another way of asking this same problem. would be something like this, where I ask you to factor the polynomial x cubed plus 2x squared minus 13x plus 18, given that x minus 1 is a factor. So the trick here is I'm going to use the factor remainder theorem. Since I know x minus 1 is a factor, I know that when I divide these two things, I'm going to get a remainder 0, right? Everybody agree with that? So I'll just start by doing the division, knowing that I'm going to get a remainder 0 here. Oh. Gee golly willikers. I copied this down wrong. That's more like it. Okay. Everybody good there? Now that I made some corrections and have the right numbers in all the right spots. Got a remainder 0. That's good. In fact, I knew that was going to happen because already from the given part in my question, I knew that that polynomial is going to be x minus 1 times something else, right? I was told in the problem that this was a factor. I confirmed it by doing the division and getting a 0 remainder. So I double knew that that is a factor. What I'm more interested in, though, is what times x minus 1 is going to give me that polynomial back. Well, the quotient tells me. Everybody okay there? Is x squared plus 3x minus 10 factorable? Yes. What does it factor to? Good. So x plus 5, x minus 2. Is this polynomial at the end always going to be factorable? No, it might not be. It could be. A lot of times it would be, but it doesn't have to be, right? Because we know there are some quadratics that are not factorable. And that's okay. You might just not be able to go any further. Or you might be able to go all the way down. Everybody's okay with that? What if I ask you then to solve x cubed plus 2x squared minus 13x plus 10 equals 0? Well, I know the factored form for it already, right? Yeah, so then I just set each one of these equal to 0. And it's an easy, right? The hard part is getting it factored. Once it's factored, the solving, that's a piece of cake. We're going to stop here.